All right, so third simple example of stoichiometry. We're told when heated in air, mercury will react with oxygen to produce mercury 2 oxide. And if 2.7 milliliters of mercury is reacting this way, what mass of mercury 2 oxide will be produced? So we want to identify our given quantity. What's the given quantity here? 2.7 milliliters of mercury is my given quantity. All right, and what am I asked for? Mass of mercury 2 oxide. All right. So I'd start with my 2.7 milliliters. Is that what it was? All right, 2.7 milliliters. And I need to get that to moles. So, all right, I have a volume, so I'm going to use 22.4. No, I'm not going to use 22.4. Yeah. I'm yelling at myself. Thank you. Everyone in the room was like, why would you do that? So thank you. But I'm just saying, people do it all the time. They're given a volume, and they're like, oh, 22.4. 2.7 milliliters. What am I going to do with 2.7 milliliters? I'm going to change that into centimeters cubed. All right, so 1 centimeter cubed is 1 milliliter. All right. And then what am I going to do with centimeters cubed? Divide by the density. So the density is 14.2 grams per centimeter cubed. All right. So this is really going to give me grams of mercury. So then once I have grams of mercury, got to go to moles. How do I get to moles? There's 1 mole of mercury for every 200.6 grams. All right. Now, once I have grams or moles of mercury, what do I need? All right, I need a stoichiometric equation. I need a balanced chemical equation. So it's mercury liquid is reacting with oxygen gas, making mercury 2 oxide. All right, what is mercury 2 oxide? Well, mercury 2 is going to be Hg2 plus. Oxide is O2 minus. So the formula is just going to be HgO. And to balance it, I would need 2 Hgs and 2 HgOs. Or another way to balance that would be to have one of these, 1/2 of these, and one of these. Either one of those things would be acceptable. Doesn't matter. So I need the ratio of mercury to mercury oxide. Well, that's simple. What is it? 1 to 1. And then I would finish it off by going to the quantity asked for, which was mass. So there's 216.6 grams of HgO for every 1 mole of HgO. And my mathematical answer is sorry, 41.4 grams of HgO. All right. So that's our process. Get to moles, Moles of one thing, moles of the other. Get to the quantity you're asked about. First twist we can put on a problem like this is we give you the amount of both reactants, and we don't tell you which one is going to run out first. So the way I always think of this is it's like a problem where you say you have 100 pieces of turkey and 150 slices of bread. How many turkey sandwiches can you make? You've just got to figure out, okay, which one of these two things am I going to run out of first? And that'll limit my sandwiches. So you're given the amounts of both reactants. You got to figure out which one runs out first. The way I tend to do this is I calculate the amount of product that I could make from the first reactant. I calculate the amount of product that I could make from the second reactant, and then I choose the smaller number. There are other ways to go about solving a limiting reactant problem. But that's the way I tend to do it. So my approach would be to calculate amount of product I could make from each reactant individually. And then choose the smaller answer. Because if I have enough bread to make 75 sandwiches and I have enough turkey to make 100 sandwiches, I can only make 75. And then I'm done. Or I could be creative and I could skimp on the bread and maybe, I don't know, make those fold over sandwiches. Or put more turkey in each sandwich. But in chemistry, everything's got to be in fixed ratios. So with stoichiometry, I don't have those creative options. All right, so going back to this problem, I'm going to have to do two independent calculations. I'm told I have 1 kilogram of calcium phosphate and 1 kilogram of concentrated H2SO4. I'm going to have to do a calculation independently for each of those things. I'll calculate the amount of product I can make from each one, and then I'll choose the product that gives me the smaller amount of, choose the reactant that gives me the smallest amount of product. So my first given quantity would be 1 kilogram of calcium phosphate. So if I start with 1 kilogram, I'll make it 1,000 grams of calcium phosphate. First step is going to be to go to moles. To get to moles, I know there's going to be 1 mole of calcium phosphate for every how many grams? 310. All right. I'm asked about calcium sulfate, so I want a relationship of moles of calcium sulfate to moles of calcium phosphate. So I go back to my equation and I see, oh, there's no coefficients. So what do I have to do? Make them. All right. So what coefficients will make this reaction work? All right. So I have my balanced equation now. Looks like my ratio is going to be 3 to 1. Now, I could cut my calculation off there. I could calculate the amount of moles of calcium sulfate I can make from each reactant and then do a final calculation where I convert that back to grams. I like to just convert all the way to the amount of product that I'm asked for from each of my reactants and then choose a smaller one. So my next step would be to turn this into grams. So how many grams of calcium sulfate are in a mole? 136. All right, so that's going to give me how many grams of calcium sulfate? Derek? All right. All right. So my second reactant that I'm given is 1 kilogram of concentrated H2SO4. What that means is concentrated H2SO4 solution, and I'm told it's 98% H2SO4 by mass. So what does that mean if I have 1,000 grams of that solution? How many grams of sulfuric acid is it actually? 980, because the 98% means that there's 98 grams of H2SO4 for every 100 grams of solution. So I have to do that additional step just to get the mass of H2SO4 that I have. Now that I have the mass of H2SO4, next step, got to go to moles. So there's 1 mole of H2SO4 for every, what is that, 98 grams? Oh, so far the math is working out pretty easily because the 98s are going to cancel. My ratio from the equation is that there's 3 moles of CaSO4 for 3 moles of H2SO4. So I have a 3-to-3 ratio. And the last step's going to look the same, 136 grams of calcium sulfate for every 1 mole. Well, I can do that math in my head. '98s cancel out. The 3's cancel out. So I get 1,000 divided by 100, which is 10 times 136. So that would be a problem that you could solve on the multiple choice section of the AP test without a calculator. You need to be able to calculate molar masses, which you should be able to do by adding, 1 and 2 digit numbers by hand, sure. Well, the multiple choice question wouldn't be this whole question, but it could be, this second calculation. Definitely could be a multiple choice question. Now, to get to your point of complaining about having to add up the molar masses, a lot of times they give you the relevant molar masses in the problem. And so it's really just about setting it up and then seeing where things cancel. All right, so I have these 2 amounts. If all of my calcium phosphate reacts, I'll get 1320 grams. If all of my sulfuric acid reacts, I'll get 1360 grams. How much can I actually make? 1320. Most common mistake that I would see here, what do you think is the most common mistake I would see? Adding them together. So every once in a while we'll find people adding these two numbers together and saying you could make 2,680 grams. But you're missing the point if you do that. That's where you're saying if you have enough bread to make 75 sandwiches and enough turkey to make 100 sandwiches, then you can make 175 sandwiches. It doesn't work that way. So this is the maximum amount that can be made. And the limiting reactant would have been calcium phosphate. So a limiting reactant problem is really just two straightforward stoichiometry problems followed by a choice. That's it. Questions there? All right. So then the last part is when we run reactions, they don't exactly turn out the way the stoichiometry predicts. And I know you might not like it that I keep using the same analogy, but let's say we were running a sandwich shop and we go out and buy a bunch of bread and we buy a bunch of lunch meat and we theoretically have enough bread and enough lunch meat to make 1,000 sandwiches, right? But then we hire a bunch of teenagers to actually run the sandwich shop. And what's going to happen? Well, some of the bread, some of the materials they might eat, some they might drop on the floor and then throw away, some they might give to their friends. So the same thing happens in a chemical reaction. You can calculate, all right, this is how much of the product I should make, but there are side reactions that can happen. So there are other things that could happen that use up some of your reactants. Some might get spilled along the way. So you might say, well, we weighed out 5 grams of reactant, but maybe only 4.9 grams of it made it into the reaction vessel. Sometimes reactions just don't go to completion. And so the theoretical yield is the maximum amount that you calculate based on stoichiometry. All right. So theoretical yield is the maximum amount based on stoichiometric calculations that can be made from the reactants. Yeah. So student question is, could you go over the theoretical yield if you accidentally spill in extra reactant? I suppose if you happen to spill in extra of both reactants, I suppose in general that's not what's observed. All right. In general, if you run a reaction and you get greater than 100% yield, probably you haven't purified your product effectively. So that's usually the conclusion. If you go on and you take organic chemistry at some point, which I hope you all do, in the organic chemistry lab, you take some starting material, you run a reaction at the end of the lab period, which is usually going to be like 5 hours. You isolate that product, and then you weigh it, and you decide, oh, what was our yield? And then you test its melting point. Testing melting point is a way to a very rough measure of purity. So if you have a pure substance, it should melt at a specific temperature. The more impurities you have, it's going to bring the melting point down, and it's also going to cause it to melt over a wider range of temperature rather than all at the same time. And so a lot of times at the end of an orgo lab, people will say, oh, I got 110% yield, but my melting point was like 15 degrees lower than it should have been. And the reason is it just hadn't been purified. Okay. So theoretical yield is the maximum amount that you can make. The percent yield would be what percentage of that did you actually make. So it's going to be, you calculate that by taking the actual yield, the actual amount made, divided by the theoretical yield, times 100%. Times 100%. So that just converts it into a percentage. Yeah. Right. So the question is that 1.00 or is that 100%? It's 100%. So you take the fraction, multiply it by 100, that turns it into a percentage. So what does this imply about the reaction? What if I have a really high percent yield? What does that mean? In our sandwich shop, if we get a high percent yield, what would that mean about our employees? That means they did a really good job. So a higher percent yield means a more efficient reaction. Probably fewer side reactions. The reaction went to completion. Lower percent yields means the reaction is less efficient. All right, so the question is about percent yield and energetic favorability of a reaction. So this is kind of previewing where we're headed because we'll get into what role energy plays in determining how much product gets made. So reactions that are more thermodynamically favorable, more energetically favorable, will tend towards a higher percent yield, but that's not there are a number of factors, so I wouldn't necessarily correlate the two, because you can take a thermodynamically unfavorable reaction and with an input of energy, you can force it to happen to really high yield. You can also have certain reactions that are really thermodynamically favorable, but they might be competing with other reactions that are also thermodynamically favorable, and so you end up with a really low percent yield. If you're a synthetic chemist and your job is to take substances and turn them into new ones, and so if you work for a drug company and you're trying to synthesize a new pharmaceutical, part of your job would be coming up with the most efficient process you can. Now, a lot of times the synthesis might be 10 or 15 steps from the starting material to the end product. And in each of those steps, you're going to lose some. So you try and maximize the percent yield of every single step along the way, because even if you get 90% yield over the course of 15 steps, someone with a calculator out want to do 0.9 to the 15th power. Yeah, so 90% yield for each individual step. If you have 15 steps, you're down to 20% yield overall. And for a lot of syntheses, that would be really great. So percent yield is an important measure of how efficient a reaction is, and a chemist usually tries to maximize their percent yield, with the caveat that, like we said earlier, sometimes you can artificially inflate your percent yield by making an impure product, and so it makes it seem like you got a better yield than you did. So when we talk about percent yield, we're talking about, all right, if you actually purify the product and calculate the actual amount of product you made. All right, so let's see. In the previous example, we calculated how much calcium sulfate could we have made. It's just a few slides earlier. 1320, so our theoretical yield was 1320. If we only made 410 grams, what should we do with all the people running our calcium sulfate shop? Fire them because they were really inefficient. This would be 410 over 1320 times 100%. What is that, about 30%? All right. I'll say 31%. That is really poor efficiency. Mr. Bennett pointed out that wouldn't be uncommon for early stage research. Yeah, but for a very simple reaction like this, between two simple compounds, that would be very poor. If you were dealing with a really complicated organic molecule and making a subtle transformation to it, 31% might be great. It all depends on context. All right, so very short unit. Let's quickly read through the things that we were supposed to accomplish and make sure we can. So can we interconvert between moles and mass, volume, temperature, and pressure of a gas, volume and molarity of a solution, number of particles? No? All right. Can you use a given amount of one substance in a chemical reaction to calculate the amount of any other substance involved in the reaction? That's just our three-step process. Go to moles, use the equation, go back to whatever unit you're asked for. Can you find the limiting reactant given the amounts of all reactants present in a reaction mixture? And calculate the percent yield. Yes, we just did that. All right. Now the AP objectives. Let's see if the language gets more complicated here. The student is able to connect the number of particles, moles, mass, and volume of substances to one another both qualitatively and quantitatively. All right, so what does that mean in English? So for instance, if you have more particles of a substance, do you have more or fewer moles of that substance? More. Oh, more particles means more moles. That would be a qualitative relationship between number of particles and moles. If you have a greater mass of a substance, does that mean you have more or fewer moles of that substance? More. Okay. So I think that's what that objective says, and then quantitatively just means do the calculations. All right. Student is able to use stoichiometric calculations to predict the results of performing a reaction in the laboratory and or to analyze deviations from expected results. So what did we calculate that would be related to deviations from expected to results? Percent yield, yeah. You know, the theoretical yield is your expected result, and then percent yield would tell you how far you deviated from it. We talked a little bit about how if you got greater than 100% yield, probably the explanation for that is impurity in your product. So I think that covers that objective. And then the student is able to relate quantities, measured masses of substance, volumes of solutions, volumes of pressures of gases, to identify stoichiometric relationships for a reaction including situations involving limiting reactants and situations in which the reaction has not gone to completion. I will say this last part, the reaction, situations in which the reaction has not gone to completion. This part we're going to talk more about in our equilibrium unit. But the first part of that, does it make sense? Basically says you can do stoichiometric calculations. All right. We'll call it a day.